When you imagine the universe, what shape comes to mind? Most of us picture a perfect sphere, a glowing ball of galaxies suspended in darkness. But what if that image is wrong? Modern cosmology suggests that space itself may be far stranger than we've ever dared to believe. The universe might not be infinite, yet it might have no edge. It could bend back on itself like a loop, or twist in dimensions we cannot see. Recent studies from the Planck satellite hint that the cosmos could in fact be slightly curved, not flat, not endless, but gently folded like fabric drawn into itself. If that's true, everything we know from the path of light to the meaning of distance will have to be rewritten, so take a quiet breath. Look up at the night sky one more time. We're about to explore the most shocking possibility of all, that the universe has a shape and it's nothing like what we imagined. Beneath the stillness of the night sky, space appears calm, flat, endless, and eternal. Yet the moment light bends, even by the smallest degree, that illusion begins to fade. We are standing on a world that curves gently beneath our feet, wrapped in the invisible fabric of space and time. Over a century ago, Albert Einstein explained that matter tells space how to curve, and space tells matter how to move. The sun does not pull the Earth the way a magnet attracts metal. Instead, it bends the grid of space itself, and Earth simply follows the curve. In 1919, when starlight passing near the sun appeared slightly displaced during a total eclipse, that faint deflection, less than 2 tiny steps of an arc on the sky, proved that space is not straight but softly bent. Imagine you are drifting just above the Earth, watching a ray of light travel beside you. It doesn't move in a perfect line. It glides along the tension of gravity like a ripple crossing stretched silk. The closer it passes to mass, the deeper the silk dips and the light slides inward, obedient but weightless. This curve repeated across every star, planet, and black hole builds the silent architecture of the universe. If you could make the shape of space visible, it would look like a slow-breathing ocean, waves rising and sinking under the weight of suns. Every galaxy leaves a shallow dent, every cluster of galaxies a valley wide enough to trap light for billions of years. Even the air surrounding you bends space ever so slightly by about 1 part in 10 raised to the power of 27 per meter, a change so small that no instrument on Earth could ever see it. To picture it another way, imagine the sun shrunk to the size of a basketball. Around that glowing sphere, space curves just enough that a beam of light racing at 300,000 kilometers each second would drift sideways less than the width of a human hair. Yet that tiny deviation controls the grand design, the orbits of planets, the pull of tides, and even the rhythm of time itself. Down near Earth's surface, where gravity deepens, time slows by a fraction of a heartbeat compared to the top of a mountain. You're already living inside that gentle asymmetry. The universe curves in silence, yet our eyes cannot see it. Only motion reveals it. The moon's orbit, a comet's sweep, the slow rotation of the Milky Way. What looks like empty space is not nothing at all. It is the soft fabric through which everything moves and endures. When we talk about the shape of the universe, we often begin with what we can see and feel, the local space around us. Gravity curves the path of light near a planet or a star, but that is only a small piece of a much larger puzzle. Local curvature is like standing on a gentle slope of a vast mountain. You can sense the incline beneath your feet, yet you cannot see the entire form of the range. To know the universe's true shape, we must step back, not by meters or miles, but by billions of light years, and ask what happens when we look at space as a whole. Imagine rising far beyond the Milky Way until the entire galaxy looks like a small silver whirlpool in the dark. Around it lie clusters, filaments, and the immense voids between them. Each of these structures curves space in its own way, yet altogether they form what cosmologists call the global geometry of the cosmos. This geometry could be one of 3 great possibilities. It may be positively curved like the surface of a sphere, where if you travel straight long enough, you return to your starting point. It may be negatively curved, shaped like a saddle, where parallel lines drift apart forever. Or it may be nearly flat, where the fabric of space stretches in every direction without ever folding back on itself. To understand these possibilities, let us picture a journey. Suppose you set off in a spacecraft always moving straight ahead. In a spherical universe, after unimaginable ages, you would loop around and see your home galaxy from behind an echo of your own beginning. In a saddle-shaped universe, you would fly endlessly, the stars thinning, never curving back. In a perfectly flat one, your path would extend forever, each destination a reflection of the same endless plane. These are not metaphors, but real geometry's maps of how distance and direction behave when gravity is woven into the structure of space itself. Yet there is another question that quietly emerges: does the universe have an edge? When we reach what we call the limit of observation, are we looking at the boundary of reality, or merely at the horizon of what light has had time to reach us? Imagine walking across the Earth. To someone on the surface, it seems flat and there is no cliff marking the end. You can travel around the planet endlessly and never encounter a wall. Many cosmologists suspect the universe may be similar, finite in volume but without a boundary, a three-dimensional surface folding back upon itself in a higher dimension. For most of our history, we believed the Earth was flat. It looked that way from where we stood, horizons straight and oceans unbroken. To the eye, there was no curve, only distance fading into haze. The illusion was not foolish. It was simply local truth mistaken for universal truth. Only when sailors crossed the oceans and stars shifted subtly with latitude did humanity begin to sense the roundness beneath its feet. The world had always been a sphere. It was our perception that was limited. Now we find ourselves repeating that same story on a cosmic scale. When we look into the night sky, the universe seems flat, stretching outward without end. Galaxies form planes. The cosmic web extends in near-perfect symmetry, and our instruments tell us that on vast scales, curvature nearly vanishes. But what we see may again be a trick of perspective, a projection of something larger than our senses can hold. Just as ancient navigators once mistook the horizon for the edge of the world, perhaps we are mistaking the limits of light for the edge of reality. You're now standing on an infinite plane. The ground beneath you feels level. You walk in a straight line for years, yet the horizon remains the same distance away. You might swear that the surface is endless, and then one day, after an impossible journey, you find yourself returning to the place where you began. The plane was not infinite. It was curved upon itself, a closed loop so vast that its curvature escaped notice. This may be the shape of the universe, finite, but without walls or boundaries, folded in a way that hides its own completeness. Our ancestors once drew maps that ended with dragons, not because monsters waited there, but because knowledge did. We too draw such maps in the dark sky above us, marking the borders of what our telescopes can see. Yet the true frontier may not be a physical line, but the limit of our imagination. Beyond that lies neither void nor wall, but continuity, a space that connects back upon itself in a quiet symmetry. So when we speak of horizons and edges, perhaps we are not describing the universe at all, but the reach of our own perception. The cosmos has no obligation to look flat merely because we stand too close to its surface. We have never truly seen the border of truth, only the boundary of our sight. And beyond that boundary, the universe continues to bend silently, endlessly within itself. In the quiet centuries before telescopes could pierce the deep sky, people believed the universe stretched forever, a vast, unchanging ocean of stars. It was a comforting thought: infinite heavens, eternal light. Isaac Newton's laws described that infinity with precision and order. To him, the cosmos was a grand mechanism balanced perfectly, each star pulling on another in a static harmony. Yet hidden within that elegance was a question that refused to rest. If space truly extended without limit, filled evenly with stars, then why is the night sky dark? Every direction you look should end at a star, just as every line drawn through an endless forest should meet a tree. The night sky then ought to blaze as bright as the surface of the sun. This is the puzzle known as Olbers' paradox, though it haunted thinkers long before Heinrich Olbers gave it a name in the 1800s. If there are countless suns, why does darkness still exist? Imagine heating a sheet of steel until it glows white hot. That should be the color of the universe in Newton's model: unbroken brilliance, an infinite furnace of light. Yet above us, the sky is mostly black, sprinkled with faint points no brighter than dust. Something about the infinite picture must be wrong. Either the universe is not eternal, or it is not filled with light in every direction, or perhaps light itself has not had enough time to reach us. Each of these possibilities hints that the cosmos has a history that it is not the fixed, eternal stage Newton imagined. For a moment, picture yourself in that older world, before the telescope standing under a sky that no theory could explain. You know the laws of gravity work on apples and planets alike. You believe the heavens obey the same principles. Yet this darkness above the quiet between stars feels like a contradiction carved into the night. You cannot measure it, but you feel it. The void is too silent, too perfect. When later astronomers began to map the stars and their faint nebulae, the paradox deepened. The further they looked, the darker space became. Infinity, it turned out, was not glowing, it was fading. Light from distant stars may have taken billions of years to travel, and the most remote galaxies were receding faster than light could keep up. The universe was not infinite in time, it had a beginning. The night sky was not bright because the stars had not always been shining. That realization cracked open the first gap in Newton's eternal cosmos. It revealed that darkness is not the absence of stars but evidence of cosmic evolution. The paradox that began as a hole in logic became the doorway to modern cosmology, a reminder that even the void between stars can speak louder than light. In the early 20th century, a quiet revolution began not in an observatory, but in the mind of a single man. Albert Einstein, working in a small office in Bern, and later in Berlin, reimagined gravity itself. In 1915, his general theory of relativity replaced Newton's invisible pull with the curvature of space-time. Mass and energy did not move through a fixed arena, they sculpted the arena itself. The universe was no longer a stage, it was a living fabric, pliable and dynamic, capable of bending, stretching and folding under its own weight. To picture it, imagine laying a heavy sphere on a rubber sheet. The sheet dips and smaller marbles roll toward it, not because the sphere calls them, but because it reshapes the ground beneath them. That was Einstein's revelation: the sun bends the geometry of space, and Earth simply moves along that curve. Time itself flows differently depending on how deep that curve becomes. Clocks near the surface of the Earth tick more slowly than clocks in orbit. Even light, the one thing Newton had declared untouchable, bows to the gravity of stars. But when Einstein applied his equations to the entire cosmos, he encountered a problem. The mathematics suggested that a universe filled with matter could not stay still. It must either expand or contract. Yet at the time, everyone, including Einstein, believed the universe to be static and eternal. To hold it in place, he added a term to his field equations, a mysterious balancing factor called the cosmological constant, pronounced lambda. This constant acted like an unseen pressure pushing outward just enough to counter gravity's inward pull. With it, the universe could remain at rest, perfect and timeless. For a few years, that adjustment seemed harmless, even elegant. But in the late 1920s, Edwin Hubble observed that galaxies were moving away from each other. The universe was expanding. The very motion Einstein had tried to cancel was in fact real. His careful constant was unnecessary and wrong. When he learned of Hubble's discovery, Einstein reportedly called it the greatest blunder of my life. Yet that blunder was not truly a mistake. Decades later, as scientists uncovered the mysterious force driving today's accelerating expansion, they named it once again with the same Greek letter, lambda, the cosmological constant reborn as dark energy. Einstein's discarded symbol had returned as the key to the universe's destiny. Imagine standing beside him in those years, looking at the chalkboard filled with curves and symbols. The equations whisper that space is not merely curved around stars, it curves everywhere, even in the emptiness between galaxies. The cosmos could be finite yet unbounded, like the surface of a sphere in higher dimensions. You cannot fall off such a surface. Travel far enough in one direction, and you might come back from the other side. Einstein's vision transformed the very idea of shape. Gravity became geometry, and geometry became the architecture of existence. Space was no longer a passive void, but a participant in the story of creation. The Earth, the Sun, the galaxies, all were notes in a grand symphony written into the curvature of space-time. And yet, just as the theory settled into brilliance, another question emerged like a ripple at the edge of understanding. If the universe can curve, can it also stretch? What if space itself is not fixed but expanding, carrying galaxies apart the way rising dough carries raisins away from one another? In 1922, a young Russian mathematician named Alexander Friedmann took Einstein's new equations and dared to let them breathe. He removed the artificial balance of the cosmological constant and allowed the mathematics to move freely. What emerged from that freedom was astonishing. The universe itself could evolve. It could expand, contract, or hover in delicate balance depending on its overall density. Geometry was no longer static, it was alive. Friedmann discovered that the shape of the universe depends on a single simple comparison: how much matter and energy exist versus how much would be needed to make space perfectly flat. From that balance came three possible worlds: closed, open, and flat. In a closed universe, space is curved inward like the surface of a sphere. If you could travel endlessly in a straight line, you would eventually return to where you began, just as a traveller on Earth might circle the globe. The universe would be finite without edge as a cosmic loop. In such a world, gravity's pull is strong enough that expansion would one day slow stop and reverse. Over immense time, the cosmos could collapse back into itself, ending in what some call the Big Crunch. Imagine flying across a great ocean of stars only to arrive once more at your own shadow from the opposite direction. That is the geometry of a universe that folds upon itself. In an open universe, space bends outward like a saddle. Parallel lines drift apart, and no matter how far you travel, you never return to your starting point. Gravity here is too weak to stop the expansion. Galaxies move away forever, and the sky grows colder with each passing eon. Picture a landscape that forever curves away from you. Every step forward leads not to a loop, but to a deeper solitude. That is the infinite negative curvature of an open cosmos. And between these two lies the delicate possibility of a flat universe. In it, the geometry follows the rules of simple Euclid parallel lines never meet, and triangles add up neatly to 180 degrees. It is balanced exactly between the two extremes, its density equal to the critical value that prevents collapse, yet avoids runaway expansion. In a sense, it is the razor's edge of existence, a universe that may stretch endlessly, yet remain poised in perfect symmetry. Each model is not merely a thought experiment, but a physical reality the cosmos could choose. The destiny of all stars all time depends on which curvature the universe carries. It is an elegant trinity, one curves inward toward reunion, one outward toward eternal dispersal, and one forever rides the narrow line between. For Friedman, these solutions were pure mathematics, but to the generations that followed, they became cosmic possibilities to be tested with telescopes and satellites. Later observations of the cosmic microwave background would measure that curvature with exquisite precision, hinting that we might live astonishingly close to the flat case balanced on the knife edge of geometry. Yet even that balance invites suspicion. If space truly appears flat, does that mean it is flat, or could it be subtly curved on scales too vast to measure? The next wave of discovery would come not from equations alone, but from the sky itself, from the faint afterglow of creation. And so as we leave Friedman's chalkboard and turn our eyes to the data of modern satellites, a new question begins to echo. Is flatness the whole truth, or just another illusion waiting to be curved? In the years after Einstein's ideas reshaped the cosmos, a new mystery emerged. If gravity could bend space, why did the universe look so astonishingly straight? The galaxies scattered around us formed a nearly even pattern, and the ancient background light, the faint afterglow of creation, was almost the same temperature wherever we looked. There were no scars of violence, no asymmetry large enough to betray an untamed beginning. It was as if the universe had been crafted with a ruler drawn across infinity. To solve this, cosmologists in the late 1970s proposed something bold, the inflation theory. They suggested that during the first moment after the Big Bang, the newborn universe expanded not gently, but explosively, stretching faster than even light could travel, not by moving through space, but by enlarging the very fabric of space itself. In a time span shorter than a heartbeat raised to the power of minus 35 seconds, the cosmos may have swollen from smaller than an atom to something larger than the Milky Way. Imagine taking a wrinkled sheet of paper full of folds and creases and pulling it from every corner until it becomes tight and smooth. That is what inflation would have done to space-time, flattening every hill, filling every valley, leaving behind a surface that appears endless. Tiny quantum ripples frozen during that expansion later became the seeds of stars and galaxies. What we see today, the filaments of the cosmic web, is the echo of those subatomic fluctuations stretched to the scale of billions of light years. 2 decades later, the Wilkinson Microwave Anisotropy Probe, or WMAP, launched into orbit to map the faint radiation left from that early fireball. Its detectors measured temperature variations as small as 1 part in 100,000. The results confirmed what inflation had promised: the geometry of space looked perfectly flat. Across the entire sky, the pattern of the cosmic microwave background formed a smooth mosaic, balanced with almost impossible precision. It was a triumph, a vision of a universe that had expanded just enough, not too little, not too much. For many scientists, this elegant picture felt complete. The universe had begun in a single breath, smoothed by expansion, and left poised in delicate equilibrium. Yet even perfection can be unsettling. Could the very smoothness that inflation created also hide what lies beneath it? If space was stretched beyond measure, perhaps its true curvature is too vast to detect, folded on scales larger than our cosmic horizon. Flatness might be an illusion born of limited sight, an artifact of perspective in a universe much greater than we can observe. Still, the evidence from WMAP was compelling, and for nearly a decade it stood unchallenged. Textbooks declared the cosmos flat to within a fraction of a percent. Students learned that geometry itself had been solved. But science is never still. New questions flickered at the edge of certainty, whispering that there might be more to see if we could look with finer eyes, colder instruments, deeper patience. Then came Planck, a satellite built with exquisite precision, capable of measuring the cosmic background with sensitivity 10 times greater than before. When Planck opened its eyes to the sky, it saw not just smoothness but the faint tremor of something else, a subtle curve where flatness was expected, a slight tilt in the great canvas of space-time. And with that, the perfect line of the universe began to quiver. When the Planck Space Observatory began releasing its final data in 2018, cosmologists around the world held their breath. This was no ordinary mission, it was humanity's most precise attempt to measure the shape of everything. For nearly a decade, Planck had been orbiting the Sun, tracing the faint whisper of the cosmic microwave background, or CMB, the ancient light left from when the universe was only 380,000 years old. Each photon Planck recorded carried the memory of how space itself was curved at the dawn of time. The earlier mission, WMAP, had already painted a picture of near perfection, a flat universe stretched smooth by inflation. But Planck's detectors were sharper, its calibration more rigorous. It measured not just temperature but the subtle polarization of light, the tiny twists and deflections caused by the gravity of galaxies bending the path of ancient photons. This phenomenon, gravitational lensing, acts like a cosmic fingerprint of the universe's overall geometry. When the Planck team compared the expected deflection of light in a perfectly flat cosmos to what they actually saw, the numbers didn't quite fit. The lensing signal was stronger, ever so slightly stronger than the flat model predicted. To make sense of the data, the researchers had to tilt the universe just a little. The best fit came when the total density parameter called omega was set to about 1.02. In the language of geometry, that meant the universe might be closed, not flat space, curving gently inward on itself like the surface of a gigantic sphere. The difference was minuscule, barely a 2% deviation, but its implications were enormous. A universe with even the slightest positive curvature could in principle be finite. If you travelled in one direction long enough, you could in theory return from the opposite side, like sailing around an invisible cosmic globe. To visualise how subtle that curvature is, imagine walking around the entire Earth, but finding that your endpoint is shifted only the width of a football field. That is roughly the scale of deviation Planck suggested, imperceptible to the eye, yet enough to alter the architecture of reality. For cosmologists, this was both thrilling and disturbing. The standard model of cosmology, known as lambda CDM, had been built on the assumption of perfect flatness. Every equation, every simulation, every prediction of how galaxies form and light travels, everything depends on that geometric foundation. And now this tiny bump in the numbers threatened to unseat it. As one researcher put it, a small curve can bend an entire theory. The Planck collaboration, cautious and precise, hesitated to claim victory. They knew the peril of overinterpreting beauty in data. It could have been a statistical fluke or an unseen bias in how the instruments read the sky. Yet the pattern was stubborn. Even when they stripped the data, reprocessed it, and compared across frequencies, the same whisper of curvature remained a quiet but consistent tilt in the great tapestry of space-time. If true, that would mean we live in a cosmos slightly closed its light, endlessly looping through the curvature of higher dimensions. The very photons Planck captured might have circled the universe more than once before arriving at our detectors, like ancient travelers returning home after billions of years. The community divided. Some called it an illusion born of noise. Others saw in it the seed of a new physics. The simplest correction, adjusting omega by 2%, could ripple through every branch of cosmology, demanding new explanations for dark energy, dark matter, and even inflation itself. What if inflation had not stretched space perfectly flat but overshot, curving it gently instead? The tension was exquisite, a universe so vast that a deviation invisible to our senses could rewrite the story of creation. Every telescope on Earth and in orbit now sought to confirm or deny that delicate arc. Yet as new measurements came in, the universe kept its silence, neither confessing its curvature nor denying it. Perhaps flatness was never meant to be perfect. Perhaps the cosmos carries its own subtle imperfection, a curvature too grand to feel too quiet to measure, but deep enough to remind us that nothing, not even the universe itself, is entirely straight. The results from the Planck mission rippled through the scientific world like a silent quake. For decades, cosmology had rested on a simple, elegant truth: the universe is flat. It was the cornerstone on which all other assumptions balanced, the geometry of infinity, the foundation of every simulation, every equation. But now that smooth foundation had developed a subtle curve, and the certainty that once held the cosmos steady began to tremble. Inside observatories and conference halls, the debate turned almost philosophical. Was this faint curvature merely an instrumental illusion, a statistical echo conjured by the noise of ancient light? Or had Planck glimpsed something deeper, a subtle truth about a universe that is not perfectly flat but slightly closed, curving inward just enough to hide its loop from view? To the public, such a small change might seem trivial. A mere 2% deviation in omega 1.02 instead of 1 hardly sounds like the collapse of certainty. Yet for cosmologists, it was like hearing a familiar melody go off key, a small imperfection in the note, but one that could alter the entire symphony. Some scientists urged caution. They argued that the data could be biased by lensing anomalies, the gravitational bending of light that Planck measured so sensitively. Others pointed to the possibility of systematic errors: the temperature of detectors, the calibration of frequencies, or even the way cosmic dust in our own galaxy might have mimicked curvature in the signal. The statistical probability of such a result, they said, could arise by chance, once in 100 trials. But others were captivated. What if the numbers were not a mistake? What if the universe truly folded slightly upon itself, a grand sphere so vast that its roundness could only be seen by instruments measuring across billions of light years? In that picture, space would be finite yet unbounded. You could travel forever in one direction, and after an eternity arrive again from behind like an explorer on a globe so enormous that no compass could reveal its curve. For those who dared to believe it, the implications were cosmic. A lightly closed universe might reshape how we understand dark energy, the mysterious force driving cosmic acceleration. Perhaps the geometry itself stores energy, and the curvature we see is a faint trace of that hidden reservoir. It might even mean that inflation, the great stretching event of the early cosmos, did not end cleanly, but left a gentle arc frozen into the structure of space-time. Among the Planck researchers, emotions were mixed. Some felt the thrill of discovery, that rare pulse of possibility when data whispers of a new frontier. Others felt something closer to unease. A universe that curves back on itself suggests a cosmos with limits, a place where infinity is replaced by a closed horizon. For those who had spent their careers describing an infinite expanse, the idea felt almost claustrophobic, as if the sky itself were folding inward. One scientist described it quietly. It feels like standing on a plain that looks endless, and suddenly realizing it might be a hill so broad we cannot see its edge. The debate remains unresolved. New experiments, DES ACT, SPT, and future CMB missions are still testing Planck's whisper of curvature, measuring again and again, searching for either confirmation or refutation. But the question has already changed something deeper. Certainty has given way to curiosity. The confidence of flatness has been replaced by wonder and a little humility. Perhaps the lesson is that even in precision we must expect imperfection. The universe may not fit cleanly into our equations. It may tilt, breathe, or close in ways that defy the neatness of theory. And maybe that is its quiet beauty. If the Planck data are true, if the universe truly carries a subtle curvature, then the shape of everything changes, not just in equations, but in meaning. A flat universe offers comfort. It stretches forever, infinite and calm. A closed universe, even one only gently curved, tells a different story. It means that space-time and destiny are all connected in a vast looping fabric. What leaves may one day return. What expands might in the far future fold inward again. Imagine walking across an endless desert, believing the horizon to be infinite. You walk for a lifetime, generations pass, and one day you find your own footprints pressed into the sand. The universe could be like that, curving so slightly that the path of light itself eventually comes home. We might already be seeing the same galaxies more than once, their images arriving through different routes across a folded cosmos, echoes of ourselves returning from the far side of space-time. To us, the world feels flat because our eyes are small. Our telescopes see less than one part in a billion of the whole, a tiny window on the skin of an unimaginable sphere. The illusion of straightness is born from limitation. Flatness is a sensation. Curvature is the truth hidden beyond our reach. If the universe is truly closed, then expansion is not endless drift, but part of a cycle, a slow breathing of creation itself. The galaxies move apart now, but in an age beyond imagining, gravity and dark energy may find a new balance. Perhaps the cosmic tide will turn, and the fabric of space will begin to draw itself inward, folding into the memory of its origin. A return not to nothing, but to the seed from which everything once unfolded. This possibility does not diminish the universe, it completes it. To exist inside a closed cosmos is to live within something self-contained, an idea that never leaks a thought that thinks itself. In such a world, beginnings and endings are the same curve viewed from opposite sides, and perhaps somewhere in that faint curvature lies a hint of design, not in the theological sense, but in geometry itself, a structure that refuses to unravel no matter how far it expands. From here the question shifts. If the universe can curve back upon itself, could it also connect to itself? Not just in curvature, but in topology. Could every straight line loop around and rejoin its own origin, making the cosmos both finite and boundless at once? That is the next mystery. The geometry of return leads naturally to the geometry of repetition, the idea that space itself might wrap, fold, and loop like a song repeating across eternity. When physicists speak of a flat universe, they don't necessarily mean infinite. Geometry and topology are not the same thing. A sheet of paper can be flat, yet if you roll it into a cylinder and join its ends, it becomes a loop, still flat locally, but finite overall. The same logic can apply to the cosmos. Space might look flat to every measurement we can make, yet still wrap around on itself, connecting end-to-end in dimensions we cannot visualize. This idea gives rise to one of the most intriguing possibilities in modern cosmology, the three-dimensional torus universe. Imagine taking a cube of space and identifying each pair of opposite faces so that they connect. Leave through one wall and you re-enter through the opposite side. Travel far enough in one direction, and you come back to where you started without ever encountering an edge. It is the cosmic equivalent of the ancient video games, where your spaceship exits the screen on the left and instantly reappears on the right. The universe could be just like that, a seamless loop, finite yet boundless, a self-connected labyrinth of straight lines that eventually circle home. To an observer inside such a universe, everything would seem perfectly ordinary. Locally, space obeys. Euclidean geometry triangles add up to 180 degrees and parallel lines never meet. But on the grandest scales, the hidden connections would begin to show themselves. A beam of light could travel endlessly, looping through space until it arrives again from the opposite direction. In theory, if our telescopes were sensitive enough, we might one day see duplicate images of distant galaxies, ghost reflections of the same object seen from multiple paths through a repeating cosmos. This model satisfies both intuition and mystery. It keeps the comfort of flatness while granting the elegance of finitude. There is no wall at the edge of existence, no cliff at the end of space, only a continuous return. The torus offers a universe that is finite but without boundaries, a kind of cosmic Mobius strip where direction itself becomes circular. To visualize it more simply, picture yourself standing on a vast plain. You walk straight ahead for 1,000,000 years, never turning, never veering off course. One day you see a faint light on the horizon. It is your own galaxy viewed from behind. Space has carried you in a perfect loop. Every direction is a circle. Every journey, no matter how straight, eventually folds back to its beginning. Mathematically, such a universe preserves the flat geometry measured by missions like WMAP and Planck. Its local curvature remains zero, yet its topology, the way space connects, is closed. Physically, that means the cosmos has volume but no edge. It can be measured but not left. This is the paradoxical beauty of a toroidal universe. To live in it is to inhabit something that feels infinite, yet is already complete. It is the cosmic version of a melody that never ends because it resolves perfectly into itself. From here, another question naturally follows. If the universe truly loops in this way, could we detect the echo of our own existence? Could could the light of our galaxy already be crossing the universe, preparing to return from the far side of the cosmic loop? Light, after all, never stops traveling. It carries the map of space wherever it goes. If the cosmos loops, then light from our own galaxy, the Milky Way might already be circling the universe, tracing vast orbits through curved dimensions and returning from the opposite direction. Somewhere in the background glow of the sky, we could in theory see ghost images of ourselves, copies of our galaxy that are not new objects but light that has made the long return trip across a self-connected cosmos. This is the logic behind one of cosmology's most haunting experiments, the search for repeating patterns in the cosmic microwave background, or CMB, the oldest light in the universe. Scientists call it the circles in the sky test. If space loops around on itself, the early radiation released after the Big Bang would have overlapped along specific paths. When viewed from Earth, those overlaps would appear as pairs of matching circles, like the faint echoes of a single drum beat heard twice. Teams using the double map and later the Planck satellite have spent years scouring the CMB for such signatures. Each pixel of that ancient glow has been examined for symmetry, rotation, and reflection, any sign that one patch of the sky might secretly be the mirror of another. The idea is simple yet staggering. If two regions on opposite sides of the sky show identical patterns, it could mean that light has wrapped around the universe and met itself again. So far, the results have been silent. No repeating circles, no doubled constellations in the cosmic afterglow. The universe, it seems, refuses to betray its loop. The simplest conclusion would be that the cosmos is too large for its repetition to fall within our observable horizon. We can see roughly 46 billion light-years in every direction, the limit set by the age of light itself. If the loop of space is larger than that, then we would never see the overlap. The ghost images of our galaxy could be wandering somewhere beyond the border of visibility, traveling paths that will not close for another trillion years. Still, the absence of proof is not proof of absence. The cosmos has a habit of concealing its symmetry until technology catches up. Astronomers now use the most powerful telescopes, the James Webb Space Telescope, the Vera Rubin Observatory, and radio arrays spread across continents to search for subtler hints, repeated alignments of quasars, identical arcs of galaxies distorted by gravity, or faint imprints in the polarization of the CMB. Each clue, no matter how faint, could reveal the loop's true scale. Imagine what it would mean if one day we found it. You gaze into the deepest field ever captured, a cluster of galaxies so distant their light has traveled for over 13 billion years, and within that cluster you see the Milky Way, our own home recorded when the sun was still young. Light from our spiral arms would have curved through the universe's hidden corridors, returning after eons to show us a portrait of our past. We would not just be observers of the cosmos, we would be one of its reflections. For now, however, the sky remains solitary. The maps of the CMB show only faint noise, no deliberate pattern, no cosmic handwriting repeating itself. If the universe loops, its curve lies beyond the reach of our instruments, its repetition too grand to detect. And yet the idea persists because it feels right, because nature loves closure, and because every straight line we know eventually finds its way back. The absence of visible echoes does not erase the possibility that they exist. It simply means the loop is larger than our vision, the circle unfinished in the space of human time. Somewhere out there, beyond the horizon of 46 billion light-years, the light of our own galaxy may already be traveling home. We may just be waiting to see it arrive. The search for cosmic symmetry does not end with loops and circles. Even if the universe repeats, it might not do so neatly. There could be a twist built into the very structure of space, a hidden rotation, subtle and disorienting, that changes our orientation each time we traverse the cosmos. This idea leads to one of the most elegant and mind-bending possibilities ever proposed, the Poincare dodecahedral universe. In this model, space is not an endless expanse or a simple torus, but a 12-face shape, each face a perfect pentagon. Picture a giant dodecahedron like a geometric jewel suspended in higher dimensions. Now imagine that every pair of opposite faces is connected, but with a rotation of 36 degrees. When you leave through one face, you re-enter through the opposite one, but turn slightly as if space itself had twisted you mid-journey. In such a cosmos, every straight path eventually returns to its starting point, yet nothing ever comes back quite the same. This twist is called holonomy, the property of space that changes your direction as you loop through it. It is as if the universe carries a built-in memory of rotation, so that every journey leaves you fractionally turned, fractionally transformed. Mathematically, the dodecahedral universe satisfies Einstein's field equations while preserving near-perfect flatness on small scales, just as Planck observed. Yet globally, it allows for closure and orientation change space as both mirror and maze. Scientists first tested this model in the early 2000s by analyzing the cosmic microwave background once again. If the universe truly followed a dodecahedral pattern, then the CMB should contain matching temperature regions arranged in pentagonal symmetry echoes of its 12 connected faces. The Planck and WMAP maps were scanned for these fingerprints for any sign that the same patch of early light appeared twice but rotated. Some early analyses hinted at weak signals, but none survived the rigor of later review. The pattern, if real, is faint enough to hide behind cosmic noise. Still, the elegance of the model remains irresistible. A closed dodecahedral universe could explain why the large-scale structure of the CMB seems slightly smaller than expected, a natural outcome of a finite cosmos with repeating geometry. In such a universe, light from the same event could reach us multiple times, each arrival rotated, producing an endless lattice of reflected skies. Imagine it for a moment. You look deep into the cosmos far beyond the reach of our galaxies, and you see something hauntingly familiar. A spiral cluster, blue and gold, twisted just slightly. You check again, it mirrors the Milky Way, but turned by 36 degrees, like the reflection of your face in a tilted mirror. If you looked far enough, you could see yourself, but rotated, reversed, transformed by the curve of creation. To stand in such a universe is to live inside a kaleidoscope of space where every line of sight bends back, not straight, but spiraling. Every photon carries not just distance, but direction, spun gently by the geometry it travels through. The dodecahedral cosmos is less like a stage and more like a dance like matter and gravity tracing loops that forever rotate in harmony. Whether it is true or not, this idea reminds us that space might be stranger than any map can show. The universe could be finite yet infinitely connected, flat yet folded, still yet spinning. If light can loop through the universe, bending and returning by paths older than galaxies themselves, then what does that say about time? Every photon that travels is a memory in motion, a record of where the universe once was. If the cosmos is truly curved or connected, then these memories never fade. They circle endlessly, revisiting their origins. In that sense, time and space are not separate, but the same reflection viewed from opposite sides of the mirror. Imagine a single beam of light leaving the heart of a star. It moves forward for billions of years, crossing the silent gulf between clusters, slipping through dark matter and cosmic dust. In a toroidal or dodecahedral universe, that beam might one day complete its journey not to an edge, for there is none, but back to the region where it began. Perhaps it will pass through us again, carrying the faint echo of its first departure. Light could become its own memory, repeating the story of creation in a quiet, endless refrain. This vision turns the act of seeing into something profound. When we look up at the night sky, we do not merely look outward, we look backward, and perhaps if the universe loops, we look inward as well. The light that reaches our eyes could be a reflection from another root, another cycle, an earlier age of ourselves. Every observation becomes a form of remembrance, and every photon a thought returning home. In a cosmos without boundaries, time itself might behave like light looping, spiraling, repeating in patterns beyond human scale. There is no first step or last breath, only the continual movement of existence folding through itself. If we could step outside this cycle for an instant, we might see that what we call past and future are simply reflections mirrored across the curvature of eternity. To live within such a universe is to live inside a thought that never ends. Each heartbeat, each wave of light, each orbit of a planet is part of the same recurring rhythm, the universe breathing, remembering, continuing. And if everything repeats, then every moment we experience may already have happened countless times before, and will happen again, carried forward by light that refuses to forget. Perhaps this is why the cosmos feels familiar even in its vastness, because we have always been here watching our own reflection shimmer across the ages. Somewhere beyond our telescopes, beyond the reach of even the most distant quasars, light from the earliest dawn still travels the curve of space searching for itself. When it finds its way back, we will see the first sunrise again, the beginning folded perfectly into the end. And from that realization arises the next great question. If the universe can remember itself through light, can it also define its own edge? Or is the idea of a boundary of an outside just another illusion, a shadow cast by our finite sight upon an infinite mirror? When people first looked up and wondered where the sky ends, the question felt simple. If we keep going far enough, must there not be a wall, a border, an end? Even now that image still lives quietly in our minds, a frontier at the edge of existence, a line where stars stop and nothing begins. But modern cosmology whispers a different truth. There is no wall and no edge, only distance and light. The observable universe, the part we can actually see, is about 46 billion light-years in every direction. That number sounds immense, yet it is not the size of everything. It is simply how far light has had time to travel since the beginning. Beyond that, the universe continues perhaps forever, but its light has not reached us. What we call the edge is only the horizon of our perception, not a physical boundary. Imagine standing on the surface of the Earth, long before anyone knew it was round. The ground beneath your feet feels flat. The horizon looks like a wall of blue sky and ocean, a limit you can almost touch. But as you walk toward it, the edge moves away. You never find a cliff or a border. The world bends beneath you, carrying you in a gentle curve. The universe behaves the same way, a cosmic sphere without a cliff. If you could sail through intergalactic space forever, you would never crash into a cosmic wall or fall into a void outside creation. You would pass galaxies drifting farther apart, their light reddened and faint until it faded into darkness, but not because there is a barrier. The darkness is only where light has not yet arrived. The frontier exists not in space, but in time. Einstein's relativity showed that space and time weave together like the surface of that Earth, curved and connected. There is no outside of the fabric, no shell holding it from beyond. When cosmologists say the universe is finite but unbounded, they mean exactly that you could in theory travel endlessly without ever finding an end. In that way, the word edge becomes almost poetic, something belonging to the limits of understanding, not of matter. The true universe has no wall, no cosmic curtain to draw aside. What we call the end of space is simply the point where our light, our instruments and our patience run out. So when you look into the night sky, remember what seems like the distant wall of stars is not the perimeter of reality. It is only the line of sight between us and what has yet to appear. There is no barrier waiting at the edge of everything. Only more space, more time, and more questions stretching quietly beyond our reach. Just as you can walk around the world without finding an end, the universe folds upon itself with the same quiet grace. No abyss, no final wall, only the endless curve of being. There is a point in the sky where even light cannot yet reach us. Not because space ends there, but because time does. The universe has been expanding for nearly 13.8 billion years, and light, though the fastest thing we know, can only travel so far. What we see when we look outward is not the structure of the entire cosmos, it is the boundary of its memory. Scientists call this the observable universe, a sphere around us roughly 46 billion light-years in radius. Everything inside that sphere is visible in principle because its photons, the ancient messengers of creation, have had enough time to arrive. Everything beyond remains hidden, not by distance alone, but by the finite age of light itself. Beyond that horizon, the story is still unfolding, written in silence, unreadable for now. This is the true meaning of a cosmic limit, not a wall, not a cage, but a temporal horizon. It marks how far light has traveled since the universe began to shine. Every time a photon reaches our telescopes, it is delivering a letter sent billions of years ago. Look at a nearby star and you see it as it was a few decades in the past. Look at a distant galaxy and you see a relic from billions of years ago. Look deep enough and you reach the moment when matter and light first parted ways, the cosmic microwave background, a faint echo of the universe, when it was only 380,000 years old. Beyond that glow, our vision fails. The fog of the early plasma blocks any view of what came before. The light simply has not traveled long enough. What lies past that boundary, perhaps new galaxies, perhaps other bubbles of space-time, remains hidden, waiting for billions of years more before its photons arrive. It is a strange, humbling thought. The edge of the universe is not a place, but a time delay. What we call the limit of the cosmos is simply the distance light has managed to tell its story. Each photon carries its own memory, a trace of where it has been and how long it has journeyed. In that sense, the boundary we see in the sky is a map of time, not of space. Imagine walking through a hall of mirrors that all reflect the past. Each step forward shows you an older image of yourself until the reflections blur into the faint shimmer of your first breath. That is what it means to look outward in cosmology. The farther we see, the younger the universe becomes, until vision itself dissolves into its infancy. And so the edge we speak of is an illusion of the present moment, Space may continue infinitely, but light cannot. The photons that define our horizon have been stretched thin by expansion, their wavelengths lengthened into gentle microwaves, their energy fading like memory whispered across eternity. The boundary is not in the universe, it is in the memory of light itself. Every night when you gaze at the faintest stars, you're not looking at distance, you're looking at time. The night sky is a diary written by photons, every page arriving out of order, each line describing an age that no longer exists. And beyond those pages, the story continues unwritten and unseen, waiting for its light to reach us, waiting for memory to complete its circle. If the universe has no wall, no outer shell, then what truly confines us? Not matter, not energy. Every time we reach a limit in cosmology, we discover it is not the universe that ends. It is our ability to comprehend what lies beyond. Imagine the surface of a calm ocean stretching endlessly in all directions. There is no cliff, no rim, only the soft curve of the horizon. You can travel forever and never find an edge. And yet every horizon hides more of the same sea folded by distance and light. The cosmos behaves this way, too smooth continuous curve through itself. The silence between galaxies is not emptiness, it is continuity. For thousands of years, humans have feared the idea of nothing beyond. We wanted a roof to the sky, a border that framed existence. But the more precisely we measure, the more the boundaries dissolve. Space does not stop where our sight stops. It simply continues without permission. In truth, there is no outside to escape to because space is not contained within something else. It is the container. Einstein once described this beautifully. The universe could be finite yet without boundaries, like the surface of a sphere. You could travel endlessly in one direction and never encounter an edge, never cross into outside. What ends is not the journey, but the language we have to describe it. When our equations reach that curve, they loop back upon themselves like thoughts trying to think their own origin. And maybe that's the real secret of a universe without edges. It forces us to face the shape of our own perception. Every time we imagine a border, it bends under the weight of new knowledge, and what looked like the end becomes another circle of understanding. There is no final frame, only the repetition of discovery. So the phrase "no boundary" is not a denial, it is an invitation. It means that knowledge itself loops through cycles, expanding, curving, returning with more depth each time. The cosmos, vast and indifferent, reflects this rhythm, a pattern of emergence, awareness and renewal. When we look up and wonder where it all stops, perhaps the universe is quietly answering nowhere. Because what we call the end is simply the beginning seen from another angle. In that way, the absence of boundaries becomes the most peaceful truth of all. No edges to defend, no beyond to fear. Only the soft continuity of being matter flowing into energy into space into thought. We are not trapped inside the cosmos. We are part of its curve, moving with it, thinking with it, remembering within it. The horizon is not a prison, it is a mirror. And somewhere in that mirror lies the next great mystery. If there is no wall to hold the universe together, what keeps its shape intact? What balances the weight of everything against the pull of nothingness? In cosmology, there is one number that quietly decides the shape of everything we see. It is called omega, the balance point of the universe, the ratio between what exists and what would be enough to make space perfectly flat. When omega equals 1, the universe stands in delicate equilibrium. Gravity pulls inward, expansion pushes outward, and space stretches straight and even in every direction. When omega is greater than 1, matter and gravity dominate. The cosmos bends inward, curving like the surface of a sphere. When omega is less than 1, expansion wins, space opens like a saddle, and galaxies drift apart forever. A single number greater than, less than, or equal to 1, yet that subtle difference determines whether the universe will expand, forever collapse into itself, or remain suspended in perfect balance. This is what cosmologists call the critical density ratio, and its precision is astonishing. Measurements from satellites such as WMAP and Planck suggest that omega is almost exactly 1, but not perfectly. It wavers near the edge like a compass needle trembling between north and nowhere. That trembling carries enormous consequence. Even a shift of 1/100th, a difference of 0.01, could change the fate of the entire cosmos. If omega equals 1.01, gravity may one day halt the expansion and pull the universe back toward itself. If omega equals 0.99, expansion will continue forever, thinning all matter into darkness. To imagine how fragile this balance is, picture balancing a marble at the peak of a mountain so smooth that the faintest breath could send it rolling down one side or the other. The universe sits on that same ridge, poised between collapse and eternity. Omega is not just geometry, it is a census of existence itself. It sums up every form of matter and energy, the visible stars and galaxies, the invisible web of dark matter, the radiation of ancient light, and the mysterious dark energy that fills the vacuum. Together they decide whether space-time bends, straightens, or folds. Every particle contributes, every photon tips the scale. At the dawn of time, this number had to be unimaginably precise. Physicists estimate that during the Big Bang, Omega must have been equal to 1 within 1 part in 100 trillion. A deviation any greater would have destroyed balance. The cosmos would have either collapsed before the first star formed, or flown apart before atoms could combine. That such precision exists at all feels impossible, like balancing the universe on the edge of a single grain of dust. Some scientists see this as proof of the inflationary era, a moment when the infant universe expanded faster than light, stretching any curvature into near perfection. Others suspect Omega may not be constant. It might evolve, subtly shifting as dark energy grows stronger. Whatever the truth, this quiet number is the universe's heartbeat. Omega decides how reality curves. It holds the story of expansion, gravity, and destiny in one fragile balance. For most of the 20th century, cosmologists believed the universe had 2 possible endings. Either gravity would one day slow its expansion and pull everything back together in a big crunch, a fiery collapse mirroring the Big Bang, or the universe would continue to expand forever, fading into eternal cold. It seemed a simple choice decided only by the value of Omega. If Omega were greater than 1, the cosmos would curve inward and eventually fall back on itself. If it were less than 1, it would open endlessly. For decades, scientists expected the balance to tilt toward gravity. The galaxies, bound by their own mass, should have been slowing down. The expansion everyone thought would eventually falter, but then the universe betrayed our expectations. In the late 1990s, 2 teams studying distant Type Ia supernovae, those stellar explosions that act as cosmic mile markers, made a discovery that stunned the world. The supernovae were dimmer than they should have been, meaning they were farther away than any existing model allowed. The universe, instead of slowing down, was accelerating. Something was pushing space apart. That something was named dark energy. Today, dark energy is estimated to make up about 70% of the total content of the universe. Ordinary matter, the atoms in stars, planets, and people, accounts for less than 5%. The rest, dark matter and radiation, fill the remaining fraction. Yet this invisible energy, spread thinly through the vacuum, now dominates the fate of everything. No one truly knows what dark energy is. Some describe it as a cosmological constant, a pressure inherent to the fabric of space-time itself. Others imagine a field dynamic and evolving, woven through every cubic centimeter of the cosmos. Whatever its form, its effect is unmistakable. It repels. It stretches space faster and faster, overwhelming the pull of gravity. This discovery changed the story entirely. A closed universe, even one with Omega slightly greater than 1, might never collapse if dark energy keeps driving the expansion. Gravity no longer guarantees a return. The cosmic dance has a new rhythm, one in which distance grows exponentially, galaxies drift beyond reach, and the night sky slowly empties itself. If this continues billions of years from now, the Milky Way and its neighbors will be all that remain visible to us. Beyond that, every other galaxy will fade beyond the cosmic horizon, carried away by the acceleration of space itself. The universe will not end in fire, but in silence, a vast dark stillness, where even light can no longer bridge the gulf. And yet there is something almost poetic in that fate. The same energy that prevents collapse also grants longevity. Without dark energy, the cosmos might have already begun to fall inward. With it, we have eons more to think, to see, to exist. It is as though the universe traded the certainty of an ending for the mystery of continuation. Physicists are still debating its nature. Is dark energy constant, or does it evolve with time? Could it one day reverse its sign, turning repulsion into attraction, bringing about a distant big crunch after all? Or will it grow stronger, tearing even atoms apart in a big rip? For now, no answer is certain, only the direction of motion. Space expands, galaxies drift. The cosmic fabric stretches like a slow, infinite breath. The The future of the universe is written not by gravity but by a whisper from the vacuum itself. Dark energy has reversed destiny. We believed that form determined fate. If the universe was closed, it would fall back upon itself. If it was open, it would drift apart forever. Geometry and destiny were twins bound by the same equations written into the same cosmic script. But with the discovery of dark energy, that bond was broken. The universe no longer obeys a single path. Its shape and its fate have parted ways. A universe can be closed in curvature yet still expand forever. It can also be flat yet doomed to a slow eternal fade. The geometry describes space, but destiny belongs to energy, the unseen force that fills the vacuum and dictates how the cosmic breath will continue. It is as if the body of the universe and its mind have learned to move separately. The body, its structure, curvature and density remains bound to gravity. The mind, its future, its pulse, its acceleration belongs to dark energy. Together they coexist, yet they no longer mirror each other. This separation feels almost philosophical, even human. For we too live between structure and motion, between what holds us and what drives us forward. The universe reflects this duality, a form that bends and a will that expands. To imagine this balance, think of a dancer moving across an endless floor. The pattern of her steps is set by geometry, the rhythm of curvature beneath her feet. But the music that carries her forward, the tempo that decides whether she slows or spins, comes from elsewhere, something unseen, something internal. Dark energy is that music, geometry is the floor, and the universe in all its vastness is the dance itself. In this light, the cosmos becomes less a machine and more a meditation, its laws intertwined yet not identical. Space can curve without closing. Time can stretch without end. Fate is no longer the shadow of structure but the echo of energy. And perhaps this is how creation sustains itself, by never allowing the equation to be complete. Each discovery opens a new gap between what we measure and what we mean. Every time we think we have drawn the final boundary, a new dimension appears softly, silently reminding us that understanding is not a destination but a motion. So now the question that remains is not what shape the universe has, but what consciousness it follows. Does space itself evolve like a living thing, responding to its own expansion? Does dark energy change as the universe grows, as if aware of the emptiness it creates? These are not questions of mathematics alone, they belong to a frontier where physics meets philosophy and where cosmology becomes almost spiritual. In this age, to study the universe is to study a paradox, a cosmos that bends yet does not return, a geometry that cannot predict its own future, a destiny unbound from the shape that contains it, form and fate like body and mind forever connected, forever apart. And beyond that realization lies the next horizon, where quantum gravity begins to whisper of the smallest threads, and space itself fractures into something more fundamental, a realm where curvature is no longer continuous, and the dance between energy and form begins anew. In the vastness, we see space seems to stretch in three familiar directions: length, width, and height, with time flowing quietly alongside. But according to string theory, this visible world is only the surface of something far more intricate. Beneath what our eyes can measure, space may have 10 dimensions, perhaps even more. In this theory, every particle, every bit of energy is not a point, but a vibrating string unimaginably small, so tiny that if an atom were the size of the solar system, a string would be no larger than a single tree on one of its planets. These strings vibrate in different patterns, and the music of their motion gives birth to everything we know: photons, electrons, quarks, all notes from the same cosmic instrument. But to vibrate in harmony, these strings need room to move, not just in the 3 dimensions we see, but in extra dimensions that are tightly folded into themselves. Physicists call this process compactification. Imagine a sheet of paper rolled so tightly into a cylinder that from far away it looks like a simple line. To the strings, those hidden folds still exist, shaping how they resonate. To us, they vanish into invisibility. If you could somehow shrink yourself down to the scale of a string about 10 to the minus 35 meters, the Planck length, you might find that every point in space contains entire curled universes, dimensions twisted into loops smaller than any particle. These curled directions may decide the laws of our reality, how forces behave, why gravity is weak, why matter clumps the way it does. This idea sounds abstract, but nature gives us hints of its truth. The electromagnetic field, for instance, spreads through invisible directions we cannot see, yet we experience its pull everywhere. What if gravity too leaks through hidden dimensions, explaining why it seems so faint compared to the other forces? In that sense, string theory isn't only about matter, it is about geometry itself becoming alive. The shape of those hidden dimensions determines the melody of the universe. If they were rolled differently, perhaps light would bend in new ways or atoms would never form. Reality then may be just one arrangement among countless possible tunes, a single song played from a vast orchestra of unseen shapes. Think of standing before a wall that looks flat and solid. You touch it, and it feels smooth. But if you could peer closer, much closer, you would see valleys and folds too tiny to notice each one shaping how light scatters and sound echoes. Our universe might be exactly like that wall, smooth at our scale yet deeply folded beneath perception. We walk through only the wide corridors of space, unaware of the rooms hidden behind its walls. The other dimensions are there compact and silent, their influence subtle but profound. They may be the reason why particles behave the way they do, and why existence itself has its particular rhythm. When we think of space, we often imagine a smooth, infinite fabric stretching, bending, curving under the weight of stars. But at the smallest imaginable scale, that smoothness begins to break apart. In loop quantum gravity, or LQG, space itself is not continuous. It is woven from tiny indivisible threads, discrete units of volume each no larger than the Planck scale, about 10 to the minus 35 meters. At that scale, distance loses its meaning. There are no lines, no surfaces, only a web of relationships loops connecting to loops, forming an intricate network known as spin networks. In this picture, space-time is not a flowing river. It is a lattice of quantum connections vibrating gently beneath the fabric of reality. If Einstein showed us that gravity is geometry, LQG takes that lesson further, saying that geometry itself is quantized. Every bit of volume, every sliver of area comes in finite steps like pixels on an invisible cosmic screen. Space cannot be infinitely divided. It is built from these granular atoms of geometry. And when you add time, the network evolves. Loops twist, merge, and reform, giving rise to a living universe where space-time is dynamic, ever-renewing. From this foundation emerges a daring idea. Perhaps the Big Bang was not the beginning. In the equations of LQG, the singularity, that impossible point of infinite density, simply disappears. Instead, as the universe contracts, its density rises until it reaches a critical limit. Then quantum pressure, born from the discrete nature of space, halts the collapse and drives an expansion anew. This is the Big Bounce, a universe that breathes, collapsing, expanding, collapsing again like the slow heartbeat of eternity. Imagine inhaling and exhaling across cosmic time. Before our universe began expanding, it might have been the rebound of a previous cycle, an older cosmos crushed and reborn. Every atom, every photon could be carrying the memory of that earlier breath. In that view, the Big Bang is not a beginning, but a transition, a pulse, a swing of the pendulum in a much larger rhythm. This concept is more than poetic. It resolves old paradoxes. It means there was never an infinite point, never a true nothing. Even in the deepest contraction, space and time retain structure. Quantum loops preserve geometry, preventing the total collapse that classical physics predicts. If the universe truly bounces, then time itself might be cyclic. The cosmos expands, ages, fades, then returns through collapse, only to rise again. Each cycle could reshape its own laws, changing slightly, learning, adjusting. It's a concept that makes existence feel less like an event and more like a pattern, an ongoing act of balance. Perhaps that is the secret LQG hints at. The universe did not explode into being. It exhaled, and before that exhalation, in some silent, unimaginable age, it had already drawn breath. If you could listen to the universe, truly listen, not with ears, but with instruments sensitive to the faintest ripples in ancient light, you would hear a hum that has lasted for nearly 14 billion years. That sound is written into the cosmic microwave background, the CMB, the oldest light still crossing the sky. To the eye, the CMB looks like a soft fog of radiation, almost uniform in every direction. But hidden within that fog are subtle fluctuations, faint variations in temperature measured in millionths of a degree. Those tiny ripples are the echoes of primordial sound waves, pressure oscillations that once moved through the hot plasma of the newborn cosmos. In those first 380,000 years after the Big Bang, the universe was a dense ocean of light and matter so tightly coupled that photons and atoms behave like a single fluid. As gravity tried to pull matter inward, radiation pushed outward. This constant tension set the cosmos ringing a vast symphony of acoustic waves rippling through the infant universe like sound through a drumhead. When the universe cooled enough for light to travel freely, those oscillations froze into the CMB patterns of brightness and darkness that record the very rhythm of creation. By studying their frequencies, cosmologists can hear the geometry of space itself. A flat universe produces a distinct harmonic structure. The peaks in its power spectrum line up at precise intervals like notes on a well-tuned instrument. If the universe were curved closed or open, those peaks would shift, the chords would detune, and the cosmic music would sound ever so slightly different. It is in a sense cosmic acoustics, listening to the shape of everything by reading its vibration. Each peak in the CMB's frequency map tells a story how matter clustered, how dark energy rose, how gravity sculpted the earlier structures. Through this harmonic code, we learn that our universe is almost perfectly flat, its notes aligned, its melody nearly pure. But nearly is not the same as exactly. There are whispers in the data, slight deviations, unexpected beats that could hint at a subtle curvature or perhaps at something deeper, a cosmic topology, a space that loops back on itself in ways our instruments cannot yet detect. To study the CMB is to eavesdrop on time itself. Those ripples of light carry the memory of a universe still learning to expand, a universe that once resonated like a living instrument. And somewhere hidden in that ancient harmony may lie the key to its true shape. Perhaps the cosmos continues to sing its melody, stretching across epochs, fading into the low hum of the microwave background, a sound too deep for human ears, but clear enough for mathematics to translate. We are in the end listeners to a vast and ongoing resonance. Through vibration, the universe speaks of its own structure, and by hearing it, we begin to remember that space itself has a voice. There are only two great possibilities left for the shape of everything. Either the universe is infinite, stretching without end, or it is finite yet without boundaries, a closed hole that loops gently upon itself. If the universe is infinite, then every arrangement of matter must repeat somewhere. Somewhere unimaginably far away, another version of you may be reading these very words, a mirror Earth, orbiting a mirror Sun, in a distant arm of a mirror galaxy. In an infinite cosmos, every possibility becomes inevitable. Every pattern of atoms reappears again and again, scattered across endless distance. Infinity has no memory, only repetition. It echoes every combination forever. But a finite universe tells a different kind of story. If space curves back on itself like the surface of a sphere or the folds of a torus, then everything belongs to a single complete whole. There are no duplicates, only connections. Light traveling far enough might return from behind you. Every direction is both forward and backward at once. It would mean that existence is self-contained, a single garden of matter and energy, enclosed not by walls, but by symmetry. Infinity is the echo, a sound that never ends, losing itself in its own reverberation. Finiteness is the garden, a space with rhythm pattern and closure, where the sum of all paths returns to the same beginning. To imagine the infinite is to face a paradox. How can something have no edge and still be real? Yet to imagine the finite without borders is equally strange. How can something end and still have no outside? Both ideas feel impossible, and yet both could be true depending on how space itself connects. Cosmology, even with its finest instruments, has not settled the debate. The Planck satellite tells us space appears nearly flat, so flat that its curvature, if it exists, is smaller than our ability to measure. That leaves both options open, infinite but unbounded, or finite but wrapped so widely that no light has yet completed the circuit. Between these two visions lies the most human question of all. Do we live in a cosmos of endless copies, or in a single self-contained creation? If it is infinite, our existence is one variation among countless others, a whisper in a hall of mirrors. If it is finite, then every photon, every life, every galaxy belongs to the same shared whole, woven into a design that, while limited, is perfectly complete. Both possibilities carry their own kind of beauty. Infinity offers freedom, the promise that there is always more to discover. Finiteness offers meaning, the comfort of wholeness, the sense that everything that exists is part of the same great curve. Because what is infinite without pattern, and what is wholeness without wonder? Every map we've ever drawn has had an edge. Edges comfort us, they tell us where the world stops and the unknown begins. But in the universe, those lines vanish. There is no border, no cliff at the end of being. Perhaps the true frontier is not in space, it is in perception. We are creatures of boundaries. We name the shore, the mountain, the end of the sky because we cannot bear the thought of limitlessness. Yet the universe refuses to obey that instinct. It curves back upon itself, turning outside into another form of within. Physicists describe this with equations, but the feeling it evokes is almost spiritual. A photon can travel for billions of years and never find a wall. A galaxy can spin forever and still reach no edge. Zoom out far enough and distance becomes curvature. Look close enough and continuity dissolves into quantum foam. Boundaries are illusions drawn by what we can measure and by what we cannot yet imagine. What we call a horizon is not a wall, it is a mirror of limitation, the point where our understanding turns back on itself. When we stare into the faint glow of the cosmic microwave background, we are not seeing a border but the outline of our own capacity to perceive. Beyond that glow, light has simply not had time to reach us, and time is not absence. It is potential waiting to be seen. So perhaps the question isn't where does the universe end, but why do we need it to? The urge for a border may come not from physics, but from psychology, from a mind that longs for containment yet lives inside the boundless. Every step of cosmology feels like self-portraiture. Each discovery redraws the frontier not of the cosmos, but of comprehension. The more we look outward, the more we find within. And maybe the true boundary, the only one that matters, is the thin line between what is known and what is still waiting to be imagined. In the end, after all the numbers and light from galaxies long gone, one question remains. What is the shape of existence itself? Maybe it isn't a sphere or a plane. Maybe existence has no geometry, only rhythm, a quiet unfolding like breath through the lungs of eternity. Every atom hums with memory. Every photon still carries the story of when space first learned to stretch. And you listening now are part of that same motion, not outside the universe, but one of its curves, a pulse of awareness through which it observes itself. Perhaps that is the hidden symmetry. All theories seek not the symmetry of matter, but of meaning. If there is no boundary, then existence must fold back on consciousness, each reflecting the other like opposite mirrors. The cosmos expands and awareness expands with it. Reality is not out there, but everywhere the act of perception reaches. Physicists call it curvature or topology. Poets call it being present's breath. Different words for the same quiet truth: the universe is whole, and that wholeness includes us. To measure space is to participate in it. To think of the infinite is to let the infinite think through us. And when that thought finally rests, what remains is not emptiness but completion. The universe doesn't end in a wall or fade into void. It ends in calm, a curve so smooth it feels like peace. Maybe that is the final geometry. The shape of existence is silence itself, not absence, but the soft pause between creation and comprehension. The quiet recognition that everything from photon to thought belongs to the same infinite breath. Let us take a step back, and the universe begins to blur. Galaxies dissolve into a faint haze. Space itself softens, turning not into emptiness but into presence. For centuries, science has tried to describe that presence. Einstein curved it, Planck measured it, and our telescopes still chase its glow through the dark. But the farther we reach, the more the map we draw begins to resemble our own reflection. Maybe that's what cosmology really is. The universe quietly learning what it looks like. Every equation, every photon caught in a mirror is the cosmos recognizing itself through awareness. The light touching your eyes tonight left its stars billions of years ago. It crossed expanding space, drifted through silence, and now ends here in you. You're not just observing the universe, you're completing its story. Perhaps that's the secret we've been circling all along, that the cosmos and consciousness are not separate. They move together, light and perception being and knowing one motion across different scales of reality. When scientists speak of expansion, they may also be describing the widening of understanding. Every discovery is not just out there, it unfolds within. Each new horizon of space is a new horizon of mind. And maybe this is why infinity feels familiar. It's not only the stars that stretch, it's awareness gently expanding into the space it once feared. When the last star fades and the final photons drift into cold, the universe won't end in darkness or silence. It will rest, folding back into the calm that began it. Imagine that stillness, no edges, No time, just a quiet pulse that once was everything. Perhaps that's what the Big Bang really was, not an explosion, but the first breath of awareness becoming matter. Now at the end of the long exhale, the cosmos returns to that breath. Not ending, not vanishing, simply remembering itself. So when you gaze into the night sky, you're not looking out, you're looking in. Every photon is a thought, every star a memory of light, and every silence between them is the soft rhythm of existence resting. Slowly, the glow fades, the universe exhales, and you, a spark of its own awareness, float with it peacefully into the same stillness that began it all.